we will get started. We are discussing conservation of mass, and that we derived the integral total mass balance equation starting from the law of physics using the Reynolds transport theorem, and then we looked at applications of that integral total mass balance equation under steady state and steady state conditions, etc. Now we are going to derive the differential form of the total mass balance equation and also look at applications of differential total mass balance equation. Okay. Now what are the applications we will be looking at after some time? We will be applying the differential form total balance equation for these kind of configurations. One is our usual flow between the two parallel plates. Another configuration is same parallel plates, but with porous walls, and then flow between a narrow gap. Another interesting example linking measurements in the ocean, and then of course the last example would be once again on transient. This differential form of total mass balance equation puts a restriction on the components of velocity. So all these examples will revolve around finding out one velocity component. Details of course we will know as we go along. So the control volumes and our experimental setups, I think we have come across this setup few times. So I have shown only the control volume which we will be using for differential total mass balance. I have not shown that for the integral balance, though. So the yellow and dashed lines represent the control volume which is now inside the equipment. That is what is to be paid attention to, either inside in the tank or in the pipe, inlet pipe, or in the outlet pipe. Okay. So the control volume, when we say for differential balance, has to be imagined a very small volume. We will see as we go along. Okay. What is the starting point for this differential total mass balance equation? We start with the integral total mass balance equation. Okay. So this was obtained from the law of physics, so which means that indirectly we are obtaining the differential balance also from the law of physics only, that we keep in mind always. Okay, let us write the integral total mass balance equation which we derived. Now I am going to apply this for a small control volume inside the equipment as shown here. A rectangular domain is shown, rectangular pipe we can say. Usually of course pipes are cylindrical, but that will lead us to cylindrical coordinate system, and within the scope of this course mostly we are going to restrict only to Cartesian coordinate system, and hence a pipe with a rectangular cross section is shown here. Okay. And a small control volume, as we have seen in the experimental setup, is also shown here. Okay. So it is a small fixed control volume. So let us write this integral total mass balance equation for a fixed control volume. We have done this when we discussed the Reynolds transport theorem. So what do? We bring in the differential sign d by dt inside the integral, and when we do that we express that in terms of partial derivative, because now the density can be a function of spatial coordinates and time. In this case, because we are integrating, after integration only time remains as the only independent variable, and hence it is d by dt. Now it is inside the integral, so rho can be a function of space and time, hence partial derivative. Okay. Of course this term remains as such. Now what is shown on the right hand side is the enlarged view of this control volume, enlarged view of this control volume. Let us see how do we discuss that control volume. Okay. First attention is on the coordinate axis. The horizontal axis is x, the vertical axis is y, and z axis points away from the board or slide or paper. Okay. Now so accordingly we have taken this control volume, and we have taken a cuboidal control volume. As I discussed, we are restricting to Cartesian coordinate system, hence we are taking a cuboidal control volume. Now, the length along the x axis is delta x, and along the y axis delta y, and along the z axis is delta z. So, those are the dimensions of the cuboidal control volume which you are considering. So, we are going to apply this form of the integral balance equation, mass balance equation. If I say mass, it means total mass as we go along, okay, because species mass has no confusion now until the very end of the course. So, let us use for simplicity mass. So, this we are going to apply this form of the integral mass balance equation for the control volume shown here. Okay. Now, what are we going to do? Express the two terms in the integral mass balance equation for this control volume. Let us take the first term. Now, in this small control volume, I say that the density has some average value rho, and when I say average value, it is the average over the entire volume, and so I can take out rho, I can take out dou rho by dou t outside the integral. Then what I left out is integral of dV, which is nothing but the volume of this small control volume, which is delta x and delta y into delta z. Okay. So, what is average value you will understand as we go along. Right now, within the small volume, I take there is a density which is an average value in the small volume, which means that average means it is constant over the entire region, and so I take this dou rho by dou t outside the integral, and integral dV becomes volume of the control volume. So, this is the expression for the first term. Now, let us consider the second term. We have seen the significance of this, let us repeat it. It represents the net rate of flow of total mass out through the control surface by convection. Okay. This is the meaning which you have discussed when you derived the integral mass balance equation. Now, if you look at the control surface, we have 6 phases here. Okay. What are the phases? If you take in terms of along axis, you have the right side face and the left side face, okay, and then you have the top face and then the bottom face, and then the front face and the rear face, okay, in terms of pairwise if you take. Now, I will express this integral for this control volume. So, if you consider the 6 phases, there are 3 outlet phases and then 3 inlet phases. What are the outlet phases? The right side is the outlet phase, the top one is the outlet phase, the front is the outlet phase. So, these are the outlet phases. What are the inflow phases? The left and then the bottom and then the rear. So, all those are the inflow phases. Now, remember we express this in terms of mass flow rate, namely m dot. We also express in terms of rho I, V I, A I. Obviously, here we should be expressing in terms of the densities and velocities and areas rather than mass flow rate. That is not significance is mass flow rate, but m dot has no importance here, okay, relevance here. Our expression, the differential equation is going to be expressed in terms of the measurable properties, namely density, velocity. So, we express the mass flow rate in terms of density, velocity. That is why expression what you see is rho I, V I, A I for the outflow phases, and similarly for the inflow phases, and then we have taken care of the negative sign ourselves instead of leaving it to V dot n. Now, second point is that we know that this expression is valid when the velocity is perpendicular to the phase. So, for all the 6 phases shown here, the velocity is perpendicular to the respective phases. Okay. So, that is why we are writing this expression. Thirdly, remember we can write this expression when the density and velocity are uniform across the area. Just like we said this rho is some average value in the volume, similarly what we will say is this rho I V I has some average value over this phase or over this any of the phases. Okay. So, that is why we write in terms of rho I V I into A I. I will just repeat the last 2 points. The way we are writing this expression implies that the velocity is perpendicular to the surface area, and that is what we have expressed as. We have shown all the velocity to be perpendicular to the respective phases. And second point is that this expression assumes that the density and velocity uniform across the surface area, and so we take some average value over the entire surface area, be it inlet, outlet, etc. Okay. Now, what we will do is these are in terms of rho and velocities, we will have to express in terms of further express this. Okay. Now, let us consider the phases pairwise. We will first take the inlet and outlet phase along x axis, then consider y axis, z axis. Okay. Okay, let us do that. Now, so considering phases along the x direction. Now, before proceeding that, let us look at the coordinates here. This left hand side we are considering phases along the x axis. So, this is the inlet phase and this is the outlet phase. Now, this phase, the inlet phase is at a x location of x. The outlet phase, because the length the length of the cuboid along the x axis delta x, the right hand side phase location is x plus delta x. Okay. So, entering phase is at x, the leaving phase is at x plus delta x. Okay. Now, what is the rate of flow of total mass entering at x? Okay. And that is given by this expression. Two ways of interpreting this expression. Number one, Vx is the velocity in the x direction multiplied by the area. What is area? This cross sectional area through which it enters, which is this delta y, multiplied by this length delta z, that is the area through which flows. So, the area of the phase is delta y delta z. So, velocity in the x direction multiplied by area, that gives you volumetric flow rate, multiplied by density gives you mass flow rate. So, we are writing expression for rate at which mass enters this control surface. Now, what is the other way of interpreting? We have seen earlier that velocity represents volumetric flux. Okay. When you derive the integral balance, we said velocity represents volumetric flux. So, when you multiply by density, you have mass flux. Of course, we know mass flux is mass per area per time. So, when you multiply by area, you are left with mass per time, which is the mass flow rate. So, two ways of interpreting: velocity into area volumetric flow rate multiplied by density, which is the mass flow rate, or the volumetric flux multiplied by density, mass flux multiplied by area gives mass flow rate. Okay. Now, coming to the nomenclature here, what I have shown here is enclosed rho and Vx into a bracket, and then I have shown a vertical line with a subscript x. What does it mean? Now, this density and velocity are changing with the spatial location. We are evaluating mass entering at the left face, for which x coordinate is x. So, this tells you that rho Vx is evaluated at x, or the value of rho and Vx at the position x. Okay. So, now let us proceed to the mass flow rate, which is leaving, and the leaving phase at x plus delta x. So, analogous expression rho Vx, but now rho Vx is evaluated at x plus delta x, the area is same. So, delta y into delta z. So, we have written expression for whatever mass entering the control volume through the left phase and leaving through the right phase. Now, what we do is write similarly expressions for mass flow rate entering and leaving through the other phases. So, for along the y axis, this is where mass flow entering, and that is given by rho V y. Now, the y coordinate of the bottom phase is y. So, we evaluated y, and along the y direction mass leaves at this phase, and so we are writing that as rho V y evaluated at y plus delta y. What is the area? The area is this delta z into delta x, that is the expression you see here, delta z and delta x is area, rho V y for entering evaluated at y, for leaving it is at y plus delta y. So, let me just show for the z direction, rho V z at z. So, which is the rear face and the area is delta x delta y, and leaving is at the front face here, okay, and rho v z at z plus delta z into delta x delta y. Okay. Just to like to mention here the text I have used here description, it says rate of flow of total mass. Okay. I could have just told written as mass flow rate. This particular nomenclature is used so that later on when you see similar statements for momentum balance, energy balance, species balance, I would say rate of flow of momentum, energy, species mass. So, same words are used so that the analogy is also becomes clear as we go along. Okay. Instead of writing mass flow rate, the words used are rate of flow of total mass, species mass, momentum, energy, etc. Okay. Now, let us put all together in the integral balance equation where we have brought in dou by dou t inside the integral sign. Okay. Okay. The first term is we simplified that as we expressed that as dou rho by dou t into the volume. Okay. Second term, remember this term as we have seen represents net outflow. So, we are writing out minus in, please keep that in mind. This is outflow and this is the inflow. Okay. Rho v x x plus delta x is the whatever mass flow leaving the right face, and this term is a mass flow entering the left face. This convention has to be kept in mind that we are writing outflow minus inflow, because thus integral represents net outflow. Okay. Similarly, I have written here expressions along the y direction, mass flow entering and leaving. Similarly, here also entering leaving, but always writing it as leaving minus entering, please keep that in mind. So, I like to mention that for sake of formality and to be in line with the usual books, derivations are done taking all the three directions into account. In terms of understanding, if you understand for one direction, most of the time you can just extend using words like analogously, similarly, you can easily extend. So, but for sake of completeness, in all the lectures we will see terms accounting for all the three directions. So, when you look at it, may look little complex, but if you focus on one particular direction, you can easily extend to other directions as well. Okay. So, let us proceed. Okay. Proceed. No? Okay. So, let us rewrite that equation here. The expression which I have seen in the last slide. Those are the terms for x direction, and then these are for the y direction, and then for the z direction as well. Okay, now, what we will do is divide by delta x, delta y, delta z, okay, and this is what we get, dou rho by dou t, and then the next two terms simplify as rho v x at x plus delta x minus rho v x at x divided by delta x. Similarly, for the y direction and z direction. Okay. If you look at this term alone, that term represents the net rate of mass flow leaving the control volume in the x direction. Okay. That is the significance of that. I tell you this because you will see how this term gets simplified, so that when you look at this term, that is what should come to your mind. It tells you that net rate of mass flow leaving the control volume in the direction, and then that is per unit volume, It is not just mass flow rate. We have in this at this stage it represents net mass flow rate leaving the control volume in the x direction, because we are divided by the delta x, delta y, delta z. In this at this stage, after dividing, it represents per unit volume. Please keep this in mind, so that when you are interpreting the physical significance of the terms in the differential equation, it will be helpful. So, once again to emphasize, at this stage of the equation they represent mass flow rate, okay, or net mass flow rate in the x direction, etc. At this stage, after dividing, they represent net mass flow rate, of course leaving per unit volume. Okay. Now, okay, of course, the first term is dou rho by dou t and other terms represent the net mass flow rates per unit volume. Now, what is that we are going to do now? Remember the differential equation, the form of the total mass balance equation which we are approaching to should be valid at every point in the equipment, of course at every instant of time. Okay. We are writing this equation at any instant of time, and for to get an equation which is valid at every point inside the equipment, we shrink this control volume. When I say shrink, that shrink should be proportionally done. For example, we say that we maintain the aspect ratio, maintaining the aspect ratio. So, this cuboid should remain as cuboid and then you shrink to a small point. So, the way you should imagine is you have a small point, but that small point has a cuboidal shape with the same delta x, delta y, delta z tending to 0. Okay. So, that is what we write formally as delta x tending to 0, delta y tending to 0, delta z tending to 0. So, the entire control volume is made to a point, but the point also the same shape of a cuboid. Okay, that is the point to be remembered. Now, sometime back we said I consider an average density in the control volume. Now, that average has now become a point value because the small control volume has become now a point. So, no longer average has to be told, just becomes a point value. In fact, if you are more formal, more precise, we should use a different symbol earlier and some other symbol now. For example, rho star earlier and rho star becomes rho. Just to avoid complexity, we use the same symbol earlier and now, but the meaning has changed now. It was rho was some average value in the control volume. Now, because we have shrunk to a point, it just becomes a point value, and that is what we are interested in. Okay. Similarly, these rho Vx values, we said they are average values across the phase, and those phase has become now a point, a small phase. So, they also become point values. So, every term, every variable in the equation has become a point value now. That is why I said you will understand this average and point value a little later. To begin with, they were all average values either over the volume or over the phase. Now, just because they become a point, the entire control volume has become an infinitesimal point. So, every variable also becomes a point value. Okay. So, now let us see what happens. Dou rho by dou t. Now, remember rho is a instantaneous value anyway, we are writing all the equations at any instant of time, it becomes a point value at every, let us say 1.1, 1.2 centimeter, 1.3 centimeter, every location you have a density. Okay. Now, what happens with the second term? Of course, very obvious, limit delta x tending to 0, some function at x plus delta x minus at x gives you the derivative. In this case, because we are considering only variation along x direction, keeping other variables constant, we result in a partial derivative dou by dou x of rho Vx. Similarly, in the y direction, similarly in z direction, of course, right hand side is 0. Okay. So, this is the differential form of total mass balance equation. We will put little more in a nice representation if we use vectorial representation. We know that rho v vector can be expressed in terms of vector as rho Vxi, rho Vy j, rho Vz k, and then the gradient vector can be expressed as dou by dou xi, dou by dou y j, dou by dou z k, which means that these three terms put together can be expressed as del dot rho v, which we call as divergence. Okay. So, there is a more short representation, simple representation of the same differential total mass balance equation. Of course, here the variables are explicitly seen, but if you want to represent in a short way, then the vectorial representation helps us. It has some other utility representing in vectorial representation, which we will see towards the very end of the course.